Good morning, everyone. We welcome everyone for the next session on battery management system design. So, I think yesterday we have discussed about the lithium-ion battery packs and the related aspects actually, and today's the discussion is going to be on battery management system. So to put it in a nutshell, what we are going to discuss today in this next 1.5 hours of related to battery management. So first thing is we will be clarifying the functionalities, the different functional requirements of a successful battery management system, right? And there is also a misconception that battery management system is only required for lithium-ion batteries. It is not like that. Today, the industry is using different types of battery chemistries, depending upon whether it is electric or a hybrid vehicle model, right? So depending upon whether it is a nickel metal hydride battery or a lithium ion battery or any other battery type, there is a need for a battery management system, and it has so many functions. So basically, in today's session, we will be discussing the design challenges for each different functionality, functional requirements for a battery management system. And more than that, we will also give some glimpse on different areas where the current trend is going on. For example, when you look at the battery management system, there are many research scholars working in this particular area throughout India. But many times I'm seeing that most of the people are focusing on the similar area most of the time, or many times people are not completely aware where to focus for the research, right? So there are many questions, blanks in there in this area, in terms of for a PhD research scholar. So we will look at battery management system in that perspective and see what are all the different scope for research in this particular domain, in this particular area of EV. And we will also talk about diagnostics and the related technology availability. And the second half, today the next session, session 2, will be on EV charging station. Actually, it was planned on regenerative braking, but it has been rescheduled to tomorrow's afternoon's second session. And today the second session will be on EV charging, since these two topics are related to both. So that's why we are replacing that topic here. So EV charging technology will be covered in the second session today, and today morning session will be with the battery management system. So before starting the session, I would like to know if any one of the participants here already working with battery management system projects or anything related to battery management system. Any faculty here or any student here or research scholar? If so, kindly you can drop a message in the chat box, exactly which area you are focusing on. Feel free to use the chat box, so you can put the message there in the chat box. So let's start the today's session. So first thing is the battery management system. So as the name suggests, it is going to manage the battery, but many times people are not aware that it is not just going to manage the battery, it is also going to manage many other components that are going to get connected with the battery, right? So it is completely managing the power flow between from the battery to other components, or from other components to the battery. So we can define battery management system even in this way. So it is something which manages the power flow, the flow of power between the from the BMS to other components, or from other components related to the BMS. So that's how we can see. So this, as everyone know, that electric vehicle uses different types of cells, and depending upon the cell chemistry, depending upon the cell, the cell cell design, right? The requirement for BMS might vary, right? So especially if you look at yesterday, we saw that the pack, a battery pack, a typical battery pack. So we saw that a typical battery pack has a number of modules connected in series, right? Or when you see this, for example, if you look at this particular module, there might be up to say 2 cells, 4 cells, or 6 cells, or 8 cells. So more number of cells might be there inside a module, and likewise there are multiple modules connected in series to make a higher voltage, basically, right? So the purpose of making multiple modules is basically to reach a higher voltage. So as you know, the industry, I told earlier that the industry is moving towards higher voltage in the sense more than 600 volt DC. So everyone are moving towards very high voltages like 800, 1000 volt DC systems, as it seems more efficient compared to the lower voltage systems. So, and it also has more advantages like better performance. And so when I say when I look at high voltage from a charger perspective, then it will increase the charging rate, the rate of charging. So quick charges are possible with a higher voltage. So many advantages are there by using a high voltage system. And so that is also one of the reason today, as the high voltage systems grow in the market, then the importance of BMS is becoming more and more increasing, right? Because as the voltage levels are very high, that more safety requirements are coming up on the functional safety standards of ISO 26262. So the new battery management system design is becoming very challenging nowadays. So look, let us understand let us understand a typical BMS, and let us see the challenges behind a BMS system. So when we look at a battery pack, as I told, we have this BMS and the related cell management controller. Say, as I mentioned, every module will have something called a cell management controller, and it is going to do some activity. We will talk about that, what are all the things it is doing with a module, right? And the battery management system, it is nothing but which connects the battery from outside world. That means a charger to the battery, or it is something that connects the inverter to the battery. It is something which connects the DC-DC converter to the battery. So it is a very key component in the battery management system. And any sort of failure, any sort of variations in the threshold values, any sort of chances of failure immediately triggers the BMS, and the BMS immediately disconnects the battery pack from the system. So it is coming under the ASIL D level of safety. As I told, ASIL D means automotive safety integrity level. So when the BMS systems are coming under the ASIL D level of design, so in automotive system, so any E&D engineer, electrical electronics engineer from electric vehicle domain, he need to design the BMS systems and algorithm, everything meeting the ASIL D level. So automotive safety integrity level D, which is like a higher safety rating. So when you look at battery BMS of a battery management system, what are the key functions? What are the key functions of a BMS? So one of these are the main functions that we can say a BMS is actually going to do. So one of the very important function is the energy and power prediction. So if we are having an electric vehicle and we need to know how this electric vehicle is behaving presently and how this electric vehicle will behave in the future, right? How these battery packs are they going to sustain for this much years, right? So all these things are possible only if we are able to accurately predict the energy and the power usage of this battery system, right? So it is very important component of the battery pack. So energy and power prediction plays a key role on the success of the electric vehicle today. So when you look at power and energy prediction, it includes battery state of charge prediction estimation, battery state of health estimation, and based on these values, they also calculate the state of power which is available in the system, and finally they will be able to calculate predict what will be the vehicle range, right? Vehicle range. So basically we should not say state of charge calculation. It is basically an estimation. It is estimated, and state of health is also estimated, right? And residual vehicle range is basically predicted based upon this estimation. So end of the day, it is the accuracy of state of charge is very, very important. If the accuracy is very poor, then what happens is the vehicle range will get affected. Can anyone tell me how, if the estimation of state of charge is wrong or it's not accurate, how it will affect the vehicle range? Can anyone uh, give some answer for this? If you have any idea? Battery state of charge, how it relates to a vehicle range. Any inputs? Any inputs from the participants? No issues. So I'll just relate that. Say when we look at the state of charge, basically, I think everyone have a mobile phone with you. And in our mobile phone, it is very clearly mentioned. So 10% of battery charge available, 20% of battery charge available. So what is that 10%, 20%? It is nothing but the state of charge. So it is a state of charge of a battery. So if our electric vehicle shows 90% in the dashboard, or in the battery state of charge, it is the state of charge of the battery, right? And basically the program, the algorithm is in such a way that if the battery charge goes below 20%, if the battery pack is having a battery charge below 20%, then immediately the vehicle will not be allowed to run in normal condition. You can say that we cannot extract the full performance of the electric vehicle. Automatically, when the battery charge goes below 20%, automatically the vehicle goes into a low power mode. We call it as a limp home mode in electric vehicle, and even conventional vehicle we have such a limp home mode. So if the vehicle goes into a limp home mode where the vehicle will not be able to perform as usual, right? So now the question is, if the state of charge which was mentioned there below 20%, which is mentioned there, what if it is wrong? What if it is wrong or it is not accurate? Or if it is more accurate, what will happen? If the state of charge is more accurate compared to the previous consideration, obviously the vehicle range will be extended, right? If the vehicle will not go to the limp home mode unnecessarily, even though the charge was there in the battery, but because of the wrong, inaccurate estimation of the state of charge, the BMS controller, microcontroller thinks that the battery is not having enough charge, and because of that, it restricts the vehicle performance. So battery SOC and its accuracy plays a very, very important role in the actual usage of the actual vehicle range. So today, many companies, they are actually suffering a lot, in this particular area only. It's a pain point, you can say, for a customer or for a manufacturer. So because the end of the day, the vehicle controller has to follow the instructions from BMS, since it is a very safety related component. So they have to follow the vehicle controller has to follow the BMS controller. BMS control will not follow the vehicle controller. It's not like that. It can get inputs, but end of the day, the decision maker is actually the BMS gives the important information to decide what to do in a vehicle, right? So because of this energy and power prediction is one of the very important function of the BMS, and its accuracy is very important. In our session, we will talk about how what are all the different methodologies that the companies are making to improve this accuracy. Second aspect is monitoring and diagnosis. So one of the another important function of the battery management system is actually to monitor the system. So measuring the voltage, measuring the current, measuring the temperature at cell level, at module level, at pack level, at different points of the battery pack. So all these things happen. That is also done by the battery management system. And detection of the isolation resistance, which is another important function of the battery management system. So isolation resistance. Say for example, if we have a battery pack, and in that battery pack there is a small cut, a damage in the cable of the battery pack, a damage in the cable of the battery pack, and because of the cable damage, there will be a leakage current, chances of leakage current flowing out of the battery system. So there will be isolation resistance lost, the insulation resistance lost in the system. So end of the day, the battery management system should be able to detect such kind of loss of isolation resistance as well. Cell leakage detection, all these things are coming under important functions of the BMS. And the other important function is actually battery lifetime enhancement. So it's not only batteries, the BMS is not only predicting the energy and power usage of the system, it is also even predicting the lifetime of the battery. That is how this state of health actually helps. So it measures the current temperature of the battery, and it measures all this data, cell balancing data, all the power usage, whether the battery is staying within a threshold value, right? And it predicts whether this battery will sustain for the designed life. Say if the battery is designed for 8 years, then this battery BMS system, battery management system, will keep on estimating the lifetime of this battery pack, and it enhances, it takes some measures as well. It takes some measures like properly managing the temperature of the battery, properly managing the voltage balancing of the cells, all these things, power limitation. So if for example, if the battery voltage, battery charge is below 20%, so if the driver is expecting very huge power from the vehicle, so this battery BMS will not provide it. It will limit the power, because if we provide the power required by the driver even below 20% SOC, this will definitely deteriorate the lifetime of the battery. So the battery management system, it not only predicts, it not only monitors certain parameter, it also does some functions to enhance the lifetime of the battery pack. That is also a very important key function done by the BMS. And finally, the communication. It not just measures and do the things, it also communicates internally and externally to a vehicle controller, or inside the BMS system itself. It communicates using different protocols. Either it uses CAN protocol, or it uses a FlexRay, or it uses a LIN protocol, right? Or sometimes it uses a normal the serial communication systems for the low end BMS components, right? So different communication protocols or techniques can be utilized in the BMS, depending upon the budget limitations, depending upon the accuracy requirements, depending upon the overall quality of the BMS, what we expect. So all these things are the driving factors towards the selection of a communication protocol. So depending upon whether we need to have a crash signal, safety related crash signal after an accident, so all these things, crash signal, it needs to be very quick, correct? It needs to be very quick, these kind of signals. So obviously we need to select a communication protocol which could be very quick, which could transfer the data at a very faster rate, right? Not like normal conventional communication protocols methods, which would be very which would be suitable for normal functions, but not a safety critical function like a crash signal, right? So all these are functions of a battery management system, a very important function of the battery management system. And finally, the very important one is the actuation. It is not only doing these functions what I mentioned here, it is also supporting on emergency actuation systems. Say not only emergency, both emergency and non-emergency. So emergency actuation includes actuation of the various contactors. If you remember yesterday, we were talking about main contactor, positive relay, negative relay, pre-charge relay. All these relays are actually controlled by the battery management system. And similarly, the coolant control. So if we have an active cooling system for the battery pack, then the coolant control, the coolant valves, all these things will be controlled, actuated by the BMS only, measuring the temperature of the battery pack. So all these are functions of a battery pack. So we can understand that a battery pack is not just doing cell balancing. Many times people, when I say BMS, they just talk about cell balancing, but it's not like that. There are more functions, many functions that a BMS is doing on a battery pack specifically. So we need to understand, we need to, there's a huge scope of work, improvement, huge scope for improvement in a battery pack from a research scholar perspective. We'll discuss more. So till here, any questions are there on the function side? Since it is very pretty much basic, most people will be aware about it, but still, if there are any questions, you can let me know here. Is there any questions? Or is it clear for everyone, these functions? So if there are any questions, feel free to drop it in the chat box at any point of time. So when we look at the battery system, the safety system specified by ISO 26262, the standard ISO 26262 represents, talks about safety of the battery pack at different level, either at BMS level or passive protection components, or from the battery cell or a battery pack, or a separator related safety concerns, the chemistry related safety concerns, and module level safety concerns. So all these are different battery pack safety or active safety considerations from ISO 26262. So basically, if any one of your research scholar working in BMS or anything related to automotive safety, I would strongly recommend you to read the ISO 26262 standard document. It is not available free of cost, but we need to pay for that. But there are many documents providing reference information about the ISO 262. If you are not able to purchase that standard, you can at least download these documents from online so that you can understand the actual requirements of the standard. And these standards, as any standard, like any standard, it gets updated timely. So time to time, kindly update the same as well. So when we look at the lithium-ion, the battery, lithium-ion battery pack, typical battery pack, we see that its temperature plays a critical role, role factor, in the whole battery function. So we see that the temperatures are of both extreme minus cold temperatures or extreme hot temperature, both are going to be a damaging aspect for the battery system. So let us look at it in a bit, in this picture gives you a better idea on different problems that might arise from a battery pack and what might be the different consequences, and where the BMS could play a role and what would be the result of it. So all these things we can explain here. So we can see here that minus 60 degrees Celsius to 10 degrees Celsius. So this is a temperature where we call it as the low temperature region, which is not acceptable for a battery pack. So yesterday we saw the operating temperature or optimal temperature range, right? So we saw that from 10 degrees Celsius to 35 degrees Celsius, it can operate, no issues, without no issues. But below 10 degrees Celsius, right, and above 35 degrees Celsius, definitely there will be some concerns. So the battery pack has to take care of it. So let us look at it. So in this picture, you can see minus 60 to 10 degree. So this is the region where it is showing. So we have issues like low temperature, low voltage, or over voltage. So in these cases, these kind of problems will arise. And the consequences basically of a low temperature is lithium plating. So it is basically a chemistry related kind of problem which is arising because of the low temperature and low voltage. Which will be at that time, when there is a low voltage scenario at a low temperature condition, then there will be a chance of anode dissolution happening. In both these cases, the BMS will be triggered. Immediately the BMS will be triggered, because the BMS will be continuously monitoring the temperature. Once the temperature goes below this threshold value of 10 degrees Celsius, immediately the BMS will get triggered. And depending upon the exact temperature value, it will decide what to do. Say, for example, if the temperature is extremely low, then it is going to turn on the heater. Or if it is acceptable, like between like -30, -20, then current shut off will happen, because at this point of time the electrolyte will be like moving towards the freezing point. So the current shut off will happen at this point, right? That's an example. And similarly, if you look at the temperatures like this, the more than 10 degrees Celsius and within below 60 degrees Celsius, that is, even that more than 60 degrees Celsius, it is like a hot climate, right? So where we see that over temperature, then obviously the overall the electrolyte layer, it gets breakdown, and we see that separation, what is a separator melts, starting separator between the anode and cathode, it will start melting. So that will lead to short circuiting of the cell, and obviously that will lead to thermal runaway end of the day. So all these conditions, the battery BMS will be into action, and it will it will either shut off the current flow from the battery pack to the other component, or it will either turn on the heater, depending upon turn on the heater or the coolant, depending upon the requirement, right? So electrolyte breakdown might happen, pressure buildup at a higher temperature, automatically the chemicals which will evaporate, and it will lead to increase in pressure buildup of the battery cell, and finally the cells will get ruptured, right? They will start becoming bulgier, and automatically, when you remember the yesterday's video, we saw that the pressure went to open, right? That's all the action of a BMS. So it's pressure went to open. It is a typical cell. It is a cell level safety measure, because the temperature is very high. At this point of time, the pressure vent will immediately open directly. So in this case, there is no instruction coming from the BMS and all. It is a cell level safety measure taken by the particular cell design itself. And finally, the oxidation of cell component. If the temperature is more than 180, 190 degrees Celsius, then the cell components will start oxidizing. Automatically, the thermal runaway will be the final event. And in this case, nothing can be done. Obviously, it is very high temperature. Nothing can be done. The whole battery pack will completely catch fire. So that's the only option, right? So the end of the day, the battery management system should ensure that this battery pack stays between this threshold, the threshold where it is healthier, and it is like it can achieve more lifetime. So end of the day, this is the challenge, of the battery pack. One of the main challenges to stay within this threshold. So the battery pack will help the BMS will help the battery pack to stay within that threshold. So that's the same information is depicted in a different way on all different thermal runaway, internal heat buildup. The same things represented here actually. So when we look at the battery, behavior in terms of the charging rate and temperature, even that is also very important, because BMS, as I mentioned, it is also going to control the charging rate and discharging rate of the battery. So why it need to control the charging rate and discharging rate of the battery? Because it has a very high level of effect on the temperature rise of the battery pack, right? And also the environmental temperature, the atmospheric temperature. Depending upon the atmospheric temperature, the battery life cycle will get reduced if we are running at a very high, faster charging rate. So this concern is definitely very important. Even in India, these issues are coming up. When we are placing the charging station in a very hot environment, hot climate, right? Obviously, the battery charging rate can't be very high. If it is very high, then it will definitely damage the battery, right? It will damage in the sense it will degrade the battery life. It will not immediately damage the battery, but instead of the battery surviving for 8 years, it might only survive for 5 years, right? Because of the issue of temperature rise, environmental temperature with the charging rate. So that is an important consideration. So you can very clearly see that 15 degrees Celsius till 45 degrees Celsius, these temperature ranges like maximum life cycle possible. Within this temperature, if the battery pack is maintained always within this temperature, definitely the battery pack could be expected to produce a maximum cycle life. But if the temperature goes below this threshold or above this threshold, obviously there will be a drop in the life cycle. You can very clearly see, and that drop in the life cycle of the battery will also get worse, worsen with respect to the rate of charging. So if we are charging at a rate of 3C, very high charging rate compared to 1C, obviously the life cycle, you can see it is like a very highly different. The life cycle, it is like from 800 life cycle, from 1200 life cycle, it is going to 800, almost 400 cycles has been dropped because of the higher charging rate. So when we have the BMS should be able to control the charging rate with respect to the temperature, which is in the environment, and the temperature of the battery pack as well. So all these are very important, right? Very important considerations. And as you see that this is an example simulation result which shows the temperature versus energy consumption. It is seen in the market, in the industry we see that there are different vehicles, electric vehicles, and you can typically see that hot temperature consumption, the energy consumption. For example, let us take the vehicle Nissan Leaf, right? So Nissan Leaf, if I say Nissan Leaf, if we can charge this battery using if there is a BMS present inside the system, and if we charge this vehicle and we see that energy consumption, right, it is around 20 plus percentage, whereas if it is a cold temperature, the energy consumption is close to 90%, right? So it is drastically increasing depending upon the temperature difference between the environment and the battery. So definitely the energy consumption, it is not going to be stable. It is going to differ from hot temperature, cold temperature. So the battery BMS is going to play a very important role in managing the temperature of the battery pack and maintaining the battery pack within the threshold temperature, so that it can improve the overall energy consumption of the battery system. So this is a thermal control diagram. Basically, the BMS is also part of it. Basically we have the result. I'm not going to talk deeper into this because tomorrow we'll be talking about the thermal management in detail. But basically the battery management system also functions in operating this valves. That is what I want to show here. So we can see that there is a four-way position electrical coolant valve. So basically these valves are operated by the battery management system only. So depending upon many times it is operated with BMS. On some cases they will have a dedicated thermal management controller as well, which is actually also part of the BMS system, but it will be like a separate dedicated controller for the thermal management will be there depending upon the size of the thermal management system, right? So this is the whole case of thermal management, right? And when we look at the other functions, right, let us understand the other functions of the battery management one by one, right? So battery monitoring system. So BMS monitors the key operational parameters such as the voltage, current, temperature, and these parameters are measured both during charging time, discharging time, and standalone conditions as well. That is very important. So based on these values, the BMS, the battery management system, estimates the values of state of the estimates the different very important values like SOC, state of charge, and state of health, and state of power. All these are very important estimations done by the BMS using these values which are taken from the battery cells, and information which is relevant for the car driver, especially if the battery SOC. What are all the information related to a driver from a BMS? Can anyone relate that? Just imagine this. What are all the information that do you think that should be given to a driver or the vehicle driver? Any idea? Any idea? Inputs from the participants? What are the information that do you think that should be notified to a driver from a BMS? Very good, very good. Thank you, Abhijit, for your answer. SOC, and one more information is any cell is getting damaged, means cell level damage means when it detects that it will not mention it as a cell level damage, but it will indicate that there is a failure, right? So we call it as malfunction indication lamp. Malfunction indication lamp. So that malfunction indication lamp will ignite. It will ignite. That will be controlled by the BMS. Any other information that do you think to be provided from the BMS? So I think Mr. Abhijit, he told SOC. So SOC could be related to the range. So not only SOC percentage it will mention, it can also mention the range of the battery pack. That means the available range. So now your vehicle is running at certain speed, and it will, the predicted range is also shown there. Like our conventional petrol diesel vehicle, how they are telling, with this current fuel, you will be able to travel 120 kilometer. With this current fuel, you will be able to travel 80 kilometers. Similarly, the battery, it will measure the SOC, and then it will predict the kilometer driving kilometer possibilities. Right? It may not be 100% accurate, but definitely that it will be better. There will be more accurate information. Anything else that do you think to be indicated to the driver? Very good. Battery is charging or discharging. Very good. So whether the battery, what state the battery is in, whether it is in a charging state or it is in a discharge state, right? That is very important. Anything else? Any added information that do you think the battery should be displaying to the system? So one of the mandatory requirements in the automotive system is the temperature control. If there should be an indicator in the dashboard for the driver to identify any sort of temperature related issues of a electric vehicle, especially on the battery pack side. Right, so they should be providing some kind of indication for a high temperature indication, so that the driver will come to know that there is a high temperature rise happened in the BMS, so that he will stop the vehicle for a rest for a period of time. Right, so that will be there. And even the as you mentioned, charging and discharging indicator, so that will be sometimes mentioned in the battery also. So when you connect the charger into a charger to the battery, immediately there will be an indication shown in the battery also, as well as the dashboard for the driver as well. All these are basically having a communication protocol in between. So they sometimes, most of the passenger vehicles, they use a CAN interface here, because it needs to be very accurate and very faster. Information has to be very latest information and very quicker. Up-to-date information should be provided. That's why most times I see that CAN interface is provided from the vehicle control unit to the BMS side. And here the data will be forwarded to the dashboard where it can be monitored. And this information includes SOC, SOH, and any error messages also. Sometimes in passenger cars, they also mention error message. For example, an error code like P001, P01CA. Like this, they will mention some error messages, and these error messages will be understandable only by the service people who will be able to service the battery management system. So these are all the things. Sometimes these error messages, basically they will not shoot up in the dashboard, but it will be it will be mentioned in the diagnostic tool, on the scan tool. So when the scan tool is inserted on the diagnostic board, onboard diagnostic system, then obviously the error messages will be shown there to the service technician. That's the thing there. So energy management and power prediction, so it prevents the battery from operating outside its safe operating area. So either it is over current, over voltage, over temperature, or under temperature. All these are actually very important key functions taken care by the battery system, right? So overcurrent in the sense, if there is a huge current withdrawn, or if the motor inverter of the electric vehicle is trying to consume a huge amount of current, over current, more than a threshold value set by the BMS, immediately that will be prevented by the BMS system. And if there is a over voltage scenario happening between the inverter to the motor, or the DC-DC converter to the BMS, right? All these cases, the BMS will prevent the system battery pack from operating. And whenever, as per the temperature information, if it notices that the temperatures are more than the threshold, or below the threshold, or above the threshold, immediately it takes the necessary action. Right. So main goal of the energy management system is to guarantee a constant supply of energy. That is very important. The battery management system ensures that the BMS ensures that the battery pack will function normally at any point of time. So that is the main key function of it. So it also measures the same in parked state, in charge state. So in parked state, for example, the battery management system enters into a sleep mode with the BMS being turned off for a period of several minutes, after which it becomes repowered to control important parameters of the battery for safety reasons. So during the parked state, it looks for, after a long drive, after a drive of say 100 km, once you turn off the electric car, immediately the BMS will start, it will just go to a sleep mode, and once again it will wake up and it will keep on watching what is the current cell balancing achieved. So if there is any cells which are not actually properly balanced, then immediately it starts internal, it starts its balancing process even during the parking state as well. And during the charging state, yes, it can also perform the same. So in the charging state, the system detecting mechanical collision on each side, during the, because in some cases, in China and other countries, during charging time, there was a vehicle accident. So we need to understand how the vehicle will behave in such kind of scenario. Obviously the BMS system also keep on watching these kind of scenarios. So if any crash or impact happens during a charging time, right, immediately the connection between the battery and the vehicle will be interrupted. So that will be one of the function of the battery management system. So the communication systems, all these things, are very important for a battery system, and we'll be talking about the communication using using their different, different topologies. Basically, I'll be talking about that in the topology side, and let me come back to the function once again later, once we finish this thing. One by one we'll go better. So pack management unit and module management unit. So you can see that there will be a overall pack level management unit, below which there will be module level. If you remember, I told cell supervisory circuit. We call it as different names are provided for that. So here we call it as module management. For every module can handle up to like 10-20 cells like that, or sometimes 2-3 cells like that. So depending upon the design, we'll talk about that. So different module management systems are there, and below which there will be every module will be managed by that, and every module will have like 4 cells, 8 cells, 10 cells like that, depending upon the possibilities, depending upon the BMS capabilities. So we see that the monitoring of the temperature, voltage of the individual cell is done by the BMS, and which is mounted directly on each battery or module stack. And high level functions such as computing the state of charge, activating the contactor, these are all high level functions, and those will be performed by the main BMS. We call it as the master BMS. And the sub-modules, the sub-modules and the main modules communicate on an internal data such as a CAN communication. So we use basically high-end vehicles other than two-wheelers. They use CAN communication for the communication between the main controller and the module level and the pack level, cell level controllers. So other important functions like charge and discharge control, right? It limits the charging voltage, it limits the discharging voltage. That is very simple thing that people will be knowing, and it also prevents the battery from deep discharging as well. So if in some cases, as I told, this will happen in India definitely. This will definitely happen in India. Already it is happening in India. What is the case? What is the scenario? Say if I'm a owner of an electric car. What I will do in electric vehicle, what I might do as a customer, Indian customer, right? My battery pack will be telling me, my BMS will be telling me that your battery pack is below 10%. So your vehicle is in a limp home mode. The vehicle will be running very slow. But still, what I will be doing, I will not be looking at it. Even if I look at it, I don't consider that as much as important. I keep on running the vehicle, even though at a slow speed. So I try to deep discharge the battery to more than certain extent, which is not actually good for the battery's life, right? Definitely this scenario is happening in India. Many times people do the same, and they say that my battery is not giving a lifetime, right? So if we exploit the battery too much, more than its limit, obviously the battery will be losing its life, and it will start degrading. Right. So very important, the BMS function is actually a deep discharging. So the BMS should actually prevent the customer from deep discharging the battery. So it should provide some kind of protection against the deep discharging. Many times today I'm seeing many two-wheeler BMS present in India by two-wheeler company, many two BMS manufacturers in India for two-wheelers. Those BMS don't have this deep discharging protection, right? That means these BMS allow the customer to drive the vehicle, electric vehicle, till 0 degree, 0% of battery. That is definitely not good for a battery pack perspective. It will definitely degrade the battery. So I think all the battery systems should, the BMS should have the feature of deep discharging capability, including the including the overcharge and over voltage capability. Thresholds basically, right? And another important function is the cell balancing. So it is a way of equalizing the charge of all the cells in the series of chain, right? So production, the cell balancing problem, it is a key issue in the battery system. And you know, this cell balancing issue might generate from the production line. This issue might happen from the production level during the manufacturing time of the battery cell itself, right? So that the weaker cell, you know, when during the manufacturing itself, if the cells are weaker, these cells will become overstressed during the charging and discharging process, and this causes them to become even weaker until they eventually fail at the end of the day. So without cell balancing, the individual cell voltages will be definitely will drift apart over time as we use it, as the charging and discharging happens in the battery system. So functions of a battery control unit of a BMS. What are the key functions? So basically we have a battery control unit, main control unit, and then we have a separate control module. For every module we have a separate controller where we will be placing the ASICs, our application specific integrated chips. All these chips will be placed here, and they make sure they measure the parameters like there are today ASICs, many ASICs like the application specific integrated circuits or chips are used in the BMS system. And earlier, you know, if you look at the BMS which was used in 2010 2011, in that particular zone, for every cell they were using one IC for the system, right? For every cell, for if there are like 100 cells in a battery pack, then 100 ICs were used at that time. And it is very difficult task to manage all these ICs, and getting a very accurate information was very difficult at that point of time. And last years, in the last few years, especially the last 3-4 years, you know, today the recent technology is developing in such a way that a single IC can monitor up to 24 to 30 cells. So which is definitely a huge advantage, a huge leap in the development of the battery management system. So today, for a pack of 100 cell, we don't need 100 ICs to manage that, right? 100 ICs to measure the voltage or the other important parameters like temperature, current, right? We can use a single IC chip and monitor up to 24 to 30 cells of a battery pack. So if it is a 100 cell pack, then just 4 ICs are possible. You know, with 4 ICs, it is possible to measure the parameters, right? So at the end of the day, it is not only you know, reducing the complexity of the BMS system, it also reduces the space occupied by the BMS, right? The conventional BMS, if it occupies too much of space on the battery, the newly developed IC chips based BMS, they are actually occupying very less space compared to the previous BMS models. So SOC and SOH estimation, we'll talk about that in depth in the coming slide. So these are all the measurements done by the BMS: cell voltage measurement, cell temperature measurement, module temperature measurement, module level voltage measurement. All these things are different measurements done by the cell and module level. And at pack level, it measures the pack level current flow from the battery BMS to the other component, and from outside to the BMS during the regenerative braking, right? It is very important for measuring the regenerative braking, right? So can anyone tell me, if the regenerative braking current is not measured by the BMS, what might happen? In what condition? Any guess? If the regenerative braking current from the inverter is, if it is not measured by the BMS, what might happen? Any example scenario can you define? Any inputs here? If the regenerative braking current from the inverter or other component to the battery battery, if it is not measured by the BMS, or if it is not monitored by the BMS, what are all the damages it can create? Think. Let us think and answer about it. Any inputs? Overcurrent, very good. But especially this will be very big problem during what case actually? Your answer is partially right. Overcurrent, and also imagine the pack is already almost fully charged. What will happen in this case? If the pack is already fully charged, and if still there is a regenerative current coming to the system, what will happen? What will happen to the battery pack? Yes. So the battery will reach its over voltage condition, and it will obviously increase the battery temperature. It will load the battery with excess input, which is not required. So if there is a BMS which monitors this particular system, monitors the current flow inside the coming from the other component, obviously it will help to disconnect the system whenever not required, right? So the regenerative braking will be disconnected whenever the system notices that the system will be connecting only when the charge availability is at a different level. And there is one more question from one of the participants, from Gopi sir. So if charging information is indicated, then it will keep on changing while regenerative braking. No, sir, I'm not telling that this charging indication will be given on the dashboard. It is, what I'm telling is, it is an indication, like light. It is just a light. It's a light which will be turning on or off during the charging condition or discharging condition. So it is like a light indicator only. So that will be like during the charging condition it will turn on, and during the discharging condition it will turn off. Yes, but it is just a light. It is just a LED. What I told. It is just an LED indicator which will be there in a battery, in a either a dashboard or in a battery itself, to indicate whether the battery is in the charging state or discharging state. So that is there existing in the vehicles present in the market. Is it clear, sir? Gopi sir? Yes. So these are all different measurements it is taking. So basically, when we look at the BMS topology, mostly across the globe today, that centralized or distributed BMS topology is typically used in the market, right? So when you look at the centralized topology, so these are all different modules. We can see this is a cell level 1, cell 2, cell 3, cell 4, and all these are connected to a central BMS. And this is basically, it is having both the monitoring unit and control unit together into a single PCB. That is the main advantage here. So both the control unit, the battery control unit, and the monitoring unit, both are present in the same system, and all the systems communicating to the central. This is the centralized BMS topology. Basically, it is having both advantages and disadvantages as well. So one of the key advantages is it is able to provide a very high speed intra-board communication, which is very beneficial to ensure a very synchronous data collection in the system. right? At the same time, it also provides a compact structure, right? End of the day, if we have a distributed BMS system, then there will be so many components, and obviously it is going to increase the number of components. So if the company aims for a very compact structure, then yes, this type of centralized BMS topology would be very advantageous, and the cost is very low, and most of the work of the BMS can be completed using only one package, and that is why it is preferably used in certain category of vehicle, right? And it produces the one of the negative, the negative point, or the what do you say, the demerit of this particular centralized system is that it produces a large number of complex wires and connectors, and it is very difficult, sometimes it is difficult to protect the battery pack when short circuits and overcurrents occur in different part of the system. And especially when considering the high voltage safety, sufficient safety clearance must be provided. Different channels, since all these things connect to the main BMS system, if the battery pack, especially for a bigger battery pack, this is going to be very challenging, right? And all components are integrated into a single PCB, resulting in a poor scalability and maintainability. That is one more problem. Thinking in terms of a manufacturer, if in case today, today we are making a BMS for, yes, this particular small car application, and now we are going to make a BMS for a bigger car application, then immediately I need to completely redesign the BMS, because the BMS cannot be immediately scaled. So the scalability is one of the drawback of the centralized BMS topology. Whereas you look at this distributed BMS topology, where the battery control unit is different and the battery monitoring circuit is different, right? So the battery, there will be a separate battery monitoring circuit for each at a module level system, and all these battery monitoring circuits will be in a CAN bus protocol, will be connected in a CAN bus protocol. So each monitoring circuit can communicate with other monitoring circuit. That is possible. So each monitoring circuit can communicate with the main BCU, battery control unit. So all these communications are possible using a CAN communication protocol. So the main advantage is, since the functions of the data collection and calculation is separated, the fault is easy to check, right? End of the day, so in this case, in a centralized topology, it is very difficult to indicate or say identify the fault, either it is within the monitoring circuit or within the control unit, right? But in this cases, it is very easy to determine the fault, where it is happening and how it has happened. It is very easy to monitor that, and the structure is very simplified, and it is having a very flexible layout, right? So if today we are making a battery pack with 20 modules, and tomorrow I am making a battery pack with 100 modules, right? I can just immediately scale the number of battery monitoring circuits. That's it, right? I can just keep on scaling the battery monitoring circuits with respect to the additional number of modules coming into the pack. I don't need to completely change the battery control unit, because the battery control unit is designed in such a way that it is flexible enough in such a way that it can handle certain number of BMCs under it, right? So we call this as the master slave concept. So it is the master BMS, which is actually doing the control unit, basically a battery control unit, and we have the slave BMS fitted to every module, which is mainly a kind of a monitoring unit. It is not going to control any aspect here. So that is the difference between different topologies present in the market, right? So let us dive deep. When you dive deep into a battery pack, this is how it is going to be look like. So this is the main battery control unit, right? And you can see that end of the day, it is going to do the functions like it is also going to measure the functions like main battery current, main isolation resistance present here, operations of the relay, interlock switches, voltage and voltage reduction, battery current reduction at pack level, not at the module level, pack level, right? All these functions are done by the main control unit, right? And for every module, as we mentioned, there will be a battery monitoring circuit, a slave circuit, which is actually called by some companies, it is called as cell supervisory circuit. So this slave units, basically, they can do multiple function. One is cell voltage measurement and temperature measurement, and cell balancing. It is also doing the process of cell balancing. So likewise, for every module, if there are 20 modules, then there will be 20 cell supervisory circuits will be there, and all these cell supervisory circuits are connected using a CAN communication, and they will be able to run, the cell balancing, which is an important function happening here. Now we need to see what is the power consumption of the cell balancing technique, right? That means what is the input, whether the cell balancing is performed by the main battery power, using the main battery power itself, or will it be performed by the external low voltage supply? What do you think? What do you think? Whether the cell balancing, if it is performed by, whether it will be performed by the battery power itself? If so, what will be the drawback and what will be the plus? And if it is performed by an external low voltage source of 12 voltage input, what will be the drawback? Or what will be the plus point? Any idea on this? I will talk about that. I'll say what is happening in the present industry. But any idea, any opinion? Cell balance, because cell balancing, it will consume some amount of milliampere current, right? Depending upon the cell balancing requirement, it will consume some milliampere current from the system. So there are two methods the industries use. One is they consume the milliampere current from the battery itself. From one battery to another battery, they will transfer this. That is like from battery usage, they do that. In some cases, they apply an external low voltage supply, 12 volt supply. So what do people think? Any inputs with this regard? Any inputs? No issues. I'll talk about that in that case. Say for cell balancing, as I mentioned today, at present in the industry, they are preferring, especially companies like Denso and Texas Instruments. All these companies are actually developing ICs, which is going to perform the cell balancing, cell voltage, cell temperature measurement, right? So these ICs are basically powered using external isolated power supply, 12 volt low voltage power supply, right? So that will be like or that is the methodology that is mostly adopted by most manufacturers today. So a separate low voltage input will be provided for providing the power from the cell balancing, right? So you can see for every module, this cell supervisor circuit will perform this function. At the same time, the main battery unit, main control unit, it takes the inputs from the current sensor, main positive relay, negative relay, and the charger related relay. All these are actually controlled by the BMU unit only, the battery control unit only. And in addition to this, HVIL unit. If you remember the first day we talked about the high voltage interlock circuit. So these interlock circuits are also actually controlled by the BMS module only, but it takes a 12 volt input in a 12 volt signal line only for these kind of applications. And throughout the crash signal, it also helps supply the CAN crash signal whenever there is a crash happening in the vehicle. We'll talk about that, what will happen in a BMS during a crash, accident, everything we'll discuss it on the last day, where we'll be talking about the testing of the electric vehicles. So there are many different cell supervision techniques. So let me show the picture and come to you. So you can see that many different cell supervisory circuits are used here. So basically we can see that these are all the cells which are present in a series, and what they will use is basically they will implement the successive approximation register converter, SAR converter, and is used basically in this kind of application if cells can be measured sequentially. Or sometimes sigma delta converters are used for permanently monitoring the cell voltage if desired. So different converters can be applied, and basically they use a sample and hold circuit. So every time the battery is in a charging state or discharging state, this sample and hold circuit, keep on monitoring the, basically what is the purpose of using this circuit? They will get the samples of the voltage value. The open circuit voltage values will be measured at every microseconds. Every microseconds, the samples of the present voltage level, present current flow in and out of the battery system, all these things will be monitored by the sample and hold circuit. And then there will be analog digital converter which would convert this into a digital information and put it in the give it to the logic circuit end of the day. So there are many different ways they can do this particular balancing technique. One is we call it as active balancing, and one of the method is called passive balancing. Today, depending upon the market, depending upon whether it is a two-wheeler application or it is a passenger car application or it is a truck and bus application, some of the companies either they go for passive charge equalization or active charge equalization. Especially at high-end vehicles, especially more than passenger car or a truck or a bus, bigger vehicles, definitely they prefer active charge because the battery pack will be very bigger in size. So the passive charge ability, looking at the passive charge ability, it is very difficult for them to maintain that. Right. So we can see these are the cells, and with this is an example of a passive charge equalization circuit. We can see there's a switch connected here and there's a resistor connected with this particular system for every cell. Right. So for every cell there will be there are different methods. For every cell they might connect a single resistor, or for a number of cells they might connect a single resistor. That's all dependent upon the IC design, what I mentioned earlier. Right. So if the IC has the capability to handle many cells at a time, right? Today, the recent model, the 2020-21, at present, the ICs which are developed by companies like Texas Instrument or Infineon, or ICs developed by what do you say? Companies like Denso, all these companies, the ICs today are having capability to handle more than 25, 30, 24, 30 cells actually at a time. So today we can see that, but end of the day, it is going to be a resistor-based equalization, resistor-based balancing. So passive balancing means what? End of the day, it is just discharging the cell, but it is dissipating the energy in the form of heat. End of the day, this energy is not going to be used for charging any other cell or a battery. So passive balancing, it means it takes the excess charge. Say for example, if this particular cell, the upper threshold is 4.2, lower threshold is 3.0. And now imagine that this particular cell is 4.2, this particular cell is 4.1. Then this particular cell should be discharged to 4.1, right? So immediately this cell will be discharged to 4.1 using this resistor and this switch combination, right? Likewise, wherever the battery cell voltage is different from the nominal voltage, then obviously the particular resistor will be operated, particular switching system will be operated by the cell supervisor circuit, and it ensures that the battery voltage is brought to the same level that all the cells are there. So basically it prevents the cell overcharging by converting the surplus energy into heat by means of the resistor. And during the discharging, on the other hand, the available energy cannot be used to prevent deep discharging of the weakest cell. So that is one of the drawback of the passive charge equalization. And where it is applicable, this passive balancing technique is mostly applicable for low-end BMS, especially in the applications like two-wheeler and three-wheeler applications, where the pack level, the pack number of cells pack will be very less, to monitor. So the capacity discrepancy of the cells will increase over time and further decrease the maximum capacity utilization. That is why this kind of passive balancing technique is not generally preferred for a application where the voltages will be like very high, more than 200, 300 voltages, right? So, but still, yes, presently in India, most of the two-wheeler, three-wheeler application, we see this passive balancing technique only applied. Right, but still there are many challenges. So I'll talk about the challenges in this particular area in the coming slide. And active charging, active balancing. Active balancing is performed using multiple methodology in a battery system today. One of the mostly used active balancing system is using the capacitive or inductive type active balancing. So they use a capacitor in connection with the battery cell, and we see a series of switches present there, and depending upon the cells available voltage value, the amount of, there will be some amount of charge taken. Say for example, if this particular cell is overcharged, and if this cell is undercharged, then obviously this capacitor will dissipate the charge from this cell and transfer that to another cell. So the capacitive and inductive approaches load the cell charge into a storage element and then transfer it to the charge which is cell which is insufficiently charged, right? So that is the methodology it adopts. And a switching matrix is basically present there. The switching matrix consists of the transistors that connects the storage element with several cells. So basically here is where the switching matrix plays a very important role, and basically it becomes very difficult to control these switches at the right point of time with respect to many different cells. So that is why today the ICs, what I mentioned, so these ICs which are going to do this balancing function, they are nothing but a combination of capacitors and inductors, right? So they are basically going to do this function, but with single IC they can do the same function for different number of cells. Say up to 20, 24, for 30 cells can be monitored or you can say balanced at a time using a single IC chip, right? So that is the advantage that the present system availability in the market. So to maintain high efficiency, this technology is mainly used for low cell numbers, especially, that means inside active balancing, capacitive cell balancing is preferred only for the lower cell numbers because of its overall cost it can end up with. And overall, the other methodology of active balancing is called transformer isolated active balancing. So in this case, they use a transformer basically in connection with the cell and switch matrix connection. So it can identify the weakest battery cell and redistribute the charge from the entire battery block. So that is how this particular system performs the transformer based, active balancing is present in system. Very rarely it has been applied. Earlier it was tried and tested, but very rarely it has been applied. And you can see, the balancing losses for one battery block are around 1.5 watt, and considerably it is lower than 18 watt for a comparable passive system. That is why, compared to a passive battery balancing system, obviously the active balancing system, the consumption of power is lesser, and even the heat generation, end of the day, as we say, losses are lesser. Obviously the heat generation in the active balancing system will also be decent. It will be a very acceptable value, which the battery management system will not have any issue. And one of the other methodology of active balancing is using a bidirectional DC-DC converter. If you remember, yesterday I've indicated that any cell can be directly charged or discharged, right, using the switching matrix between the cell and this DC-DC converter. So it is the modern, it is the very latest, recently almost all the companies are applying this type of bidirectional DC-DC converter into the BMS system, especially on the active balancing system. So where they can convert the charge from one cell to another cell using this bidirectional DC-DC converter. But still, it is all in the developmental stage. Some companies still they are improvising the performance of this bidirectional DC-DC converter based active balancing. So I would definitely strongly recommend the faculties to work in this particular bidirectional DC-DC converter based balancing technique, right? So that is these are all different key functions, key cell balancing techniques being applied there on the market. In addition to that, let me so as I told, cell state of charge estimation, it is a very important key factor, right? A state of charge estimation is to be performed. So battery SOC is equivalent to the oil meter, right? So like for a petrol diesel vehicle, how we have the meter of fuel meter. Similarly, for a battery electric vehicle, SOC is nothing but like an oil meter, right? It improves it basically it helps us to optimize the vehicle energy management, and it is a very important key factor estimated by the BMS system. There are many different estimation methods available in the market. So I'll be focusing on one estimation method, one method of obtaining this in the end of the slide. So these are all different methods of estimating the state of charge. So one is the open circuit voltage value method, impedance spectroscopy method,
or using the Kalman filter or extended Kalman filter. Different other methods are there. Basically, they come under the model-based SOC estimation methods. So today there are some companies even applying that as well. So, but most preferably they are using the Coulomb counting method in the market today. So I'll talk about that in the coming slide. So in addition to the SOC, SOH is very, very important. So SOH is nothing but it is the quantitative index to evaluate the aging degree of the battery. So if the battery is started now, say for example 2021, if we purchase this battery, how long this battery will sustain, how long at this rate of discharge and charging, how long this battery will, the life will get extended or degraded. All this information will be available when we estimate the state of health. And state of health is nothing but it is estimated from the state of charge only, right? So these are all different methods used for estimating the state of health of a battery pack. So here also we apply, depending upon the different algorithms, we apply different methods. But overall, measuring the from the SOC based from the Coulomb counting method only, we measure the upcoming the SOC and SOH, both the factors. And SOP, state of power, it is nothing but it is something which indicates the available power from the battery pack. So as I told, when your battery pack is fully discharged, right, below 20%, we cannot expect the fullest performance from the battery. And similarly, if the battery is fully charged, almost fully charged, right, we can't apply the regenerative current on the battery pack. So the state of power indicates the available power from the battery pack for a performance of the particular electric vehicle at any point of time. So many times people don't concentrate on the state of power. They just work on state of health or state of charge. But state of power is also a very important factor, which is playing a very significant role in the BMS. So I would also suggest people to work in this state of power estimation as well, right? So what are the different developments, recent developments happened in the BMS related work? One of the work I mentioned earlier is the improved monitoring, improving the monitoring IC systems. So especially Denso has done it very recently. As I mentioned, compared to the previous model, compared to the last years, 2014-15, they had a different IC design for performing the balancing in the battery system. But the recent development is that the recent ICs, they can use a single IC for monitoring many battery cells at a time. And not only that, the breakdown voltage of the batteries, ICs, these ICs have been improved from 60 voltage to 150 voltage, which is also an important factor, so that the battery, the end of the day, the ICs can withstand such higher voltages during the operation. And what is the another next trend? Next trend is wireless battery management system. Today, if you look at the, if you remember the battery pack, the initial picture that I've shown, look at this battery pack picture. We see module, and every module has a cell management controller, and every cell management controller has to communicate to the main controller. There is going to be a lot of cable utilization, right? End of the day, there is going to be a lot of cable utilization going to be present in this kind of situation. So end of the day, it is going to add cost, especially in some cases we'll be using high voltage, and some cases it will be low voltage line. So both the cases, it is going to add cost for significantly for the system, right? So today, wireless battery management system is one more key technology, which is definitely going to add many advantages in the system. So if you are a faculty research scholar, and if you are thinking to work, on the battery management system, then this is also one of the area where we can focus on. So wireless battery monitoring, battery management system, or you don't need to consider the whole battery pack as a whole. But what I would suggest is you can select a typical area of a battery cell, or a battery cell to module to pack level connection, and just focus on that particular area to convert that into wired to wireless. Right, we will understand that now in the coming slide. So what are the advantage that the wireless battery management system provides is, it provides freedom to develop a robust and reliable system. Compared to a wired battery management system, it consumes a very lower power, which is very 10 times lower power in a sleep mode for reserving energy in the cell when ignition is off. And reporting voltage, the reporting voltage and temperature data from each cell to the main MCU control unit, accuracy is very high. We need to maintain the accuracy, right? When we are moving from wired BMS to wireless BMS, obviously the challenges are more. We need to meet the new ASIL requirements. That means even though it is a wireless system, also they need to meet the automotive safety integrity level D for the best safety rating, right? So the accuracy and the ability of the wireless system to sustain for any point of time, that is very, very important. Basically, what is the key difference between a wired BMS and a wireless BMS? Wireless in the sense, will it be a completely wireless? No, they doesn't mean that it is. They don't mean it is completely wireless system. But what they mean is the wireless system applied between the cell monitoring circuit and the between the BCU, right? So between the cell to the cell supervisory circuit, it will be a wired connection, but the wireless connection is where we will be using a different instead of using a daisy chain connection, a serial daisy chain connection of all these the battery cell level cell supervisory circuits to the MCU. Instead, we can use the wireless communication channel where we can supply the information to the cloud, and from here we can transfer the information to the MCU. As I told, this wireless BMS is getting as a new trend in the market today, but it is having its more inherent challenges. So I would recommend faculties, research scholars to work in a small scale, take a small example of a cell and take a small example of a IC which is present in if you want to have a IC for this particular application, you can purchase it from Texas Instruments. So whatever I mentioned here, these are all the different IC models available in the market. So you can purchase that from the market, and you can use that for this kind of wireless BMS projects, right? Basically, this kind of wired BMS, all these things today, the trend is using the best algorithm, right? A best control algorithm. So when you look at the best, one of the best control algorithm, effective control algorithm for the BMS, which is followed is enhanced Coulomb counting method. It is the we call it as enhanced Coulomb counting algorithm, which is applied in the battery BMS today. And this enhanced Coulomb counting algorithm has many advantages, as a battery management system. It provides us very good accuracy over the estimation of the SOC and SOH values, and it also, it also adds many benefits. For example, SOC measurement during the constant charging stage or constant voltage stage, all these levels, this particular Coulomb counting algorithm has achieved a better accuracy. So how this is the typical flow chart of Coulomb counting algorithm. So today the scope of research is actually in developing a typical algorithm, statistical algorithm for the battery charging and discharging environment. So I would recommend the faculties also to focus on this particular area. You can develop your own new algorithm, or you can improve the existing algorithm available in the market, right? So there are, if you need any related research papers in this particular area, feel free to contact me to the email ID. So you can definitely, I will be able to definitely share the research papers related specifically to this particular algorithm specialization. So we can apply different algorithms. We can monitor, what you can do. What is the methodology, I would say. So basically, you can apply different algorithms. And say, for example, identify so what is basically the algorithm used in this enhanced Coulomb counting system. So first is identify the battery serial number, and if the battery serial number is same battery, it's a similar battery, no. If it's not the same battery, then determine the initial SOC value, right, the T0 value, and SOH value, and depth of discharge. All these three values will be determined by the system, and then after determination, initial determination, it will monitor the voltage and current flow inside the particular cell. And then if there is a IB value, the current flow, IB value which is measured, if it is greater than 0, it is going to be in the charging mode, and if it is less than 0, it is nothing but it is in the discharging mode. So depending upon whether the battery cell is in the charging mode or discharging mode, we have to go to the next step. If it is charging mode, then we have to say whether it is fully charged, no or yes. So if it is fully charged, yes, then in that case, the SOC is nothing but the SOH values are predicted that both the values are similar. So it's fully charged condition. And if it is like not fully charged condition, if it is not fully charged condition, then what is the present depth of discharge, that is estimated using multiple factors. And finally, the SOC and SOH is indicated here finally. And similarly, once again, this keep on happening in the circulation. Once after measurement is done, indication is done, once again go and monitor the voltage, and so keep on, this circle keeps on going at any point of operation of the battery management system, right? So you can see very clearly what is the accuracy of this algorithm when by using an experimental method and estimated SOC method. So you can see that the estimation, the accuracy is almost 3%, up to 3% difference is there in this particular using this sort of enhanced Coulomb counting method for the application directly. So you can see that on a charging stage, or during a constant current charging stage, or constant voltage charging stage, depending upon the different charging methodology, the amount of SOC estimation, the amount of SOC, everything varies. Because everyone know initially the battery gets charged using the constant charging current, and then it will, after reaching certain threshold or certain SOC level, it will go to the constant voltage methodology. So we will be talking about this in detail in the coming session, the next session actually. So that's all about the discharging mode. Even during the discharging mode also, you can see the estimated results and the experimental results are very closer. The results are very closer. That means this enhanced Coulomb counting algorithm provides a better results of the SOC and SOH, right? And not only that, the overall relationship between the lifetime and the current rate, right, with respect to the amount of current discharge, the current discharge from the battery, the 0.5C, 1C, 1.5C, 2C, the lifetime capacity of the battery pack will also be degraded. And that is basically the lifetime. In the sense, what I mean is the SOH value. The SOH estimation will also get affected. The SOH value will also get affected because of this current rating, which is also accurately determined using the enhanced Coulomb counting algorithm. So that's the present scenario in the market. And if in case any of your faculty thinking to do any testing, right? Any of the faculty want to perform any testing, you want a real-time data for your PhD research or your general research activity, and if you want to work with a collaborative project, definitely we could suggest and support. We have agencies like GARC, which is located in Chennai. So those kind of testing agencies are currently working with us for mutual projects. And even we can also work with IIT Madras on related testing and measurement activities. So wherever support is required, you can let us know. These are all different tests basically done on the battery management system or the battery pack level to characterize the battery system. Say capacity test, open circuit voltage test, and then we have the pulse power characterization test, hybrid pulse power characterization test to understand the behavior of the battery cell and pack at different charging and discharging rate, and dynamic condition test, impedance test. So all these are different tests performed for a cell or battery pack. So these are all the different equipments basically we use for such an environment. So depending upon the algorithm that we are selecting, the SOC algorithm, SOH algorithm, or the SOP prediction algorithm, or the remaining useful life prediction algorithm, RUL, we call it as RUL prediction algorithm. Based upon the different algorithm that we are going to select, the amount of tests, the number of tests necessary will be different. So all these things, are considerable factors to work on the BMS. So I would definitely recommend people to work with real-time data. Instead of just taking some reference data from papers and publishing papers, I would strongly recommend the faculty members and research scholars to take live data, real-time data from the BMS. with a live battery using hardware in loop setup or a software in loop setup, and even you can use a emulated battery system. All these are available in places like IIT Madras, GARC Chennai, and even if you can do it in a small scale, it can be developed in-house in your institute also, right? So there are many possibilities, as I mentioned, working on the wireless battery monitoring system, and working with different ICs to improve their capability to work with a higher number of cells. These are all different areas, key areas where the research is to be focused on the battery. And as I told, India's climate has its own challenges. So we need to see how the India's climate challenges are going to get affected with the BMS. So we can do all those. India specific research is also definitely recommended, right? So that's all about the battery management system. So if there are any questions from the participants, kindly drop your questions in the chat box. And here is my contact details I'm providing, because some participants requested that yesterday. So here are my contact details in the presentation, in the slide. So kindly note it down. And if you have any questions, any collaborations, any questions, anything related to EV or autonomous vehicle, feel free to reach us in any time. So definitely we'll be able to support. So any questions from participants? Any questions from participants on this battery management system side?